Let's talk about air resistance. We're going to deal with in this particular video of an object that is just falling straight down. So we have only two forces acting on it. There's weight and there's a drag force. Now, drag force gets a lot more complicated, and there's a far more complicated way of approaching it where you take into account several different factors. But what engineers, probably more than physicists, have done is they've created a shorter form of it with this variable right here, which takes into account a lot of different factors. But the general formula for drag force, this, I guess you would call it the simplified form, is 1/2 times rho c sub d a v squared. And this right here is the direction of the force, since we are dealing with a vector, and it is opposite the direction of the velocity. So I have the hat over the v to indicate a unit vector in the direction of velocity. So rho is the density of the fluid that through which the object is going. A is cross-sectional area, which is perpendicular to the velocity. So if it is falling, we're talking about this area right here, the cross-sectional area across that. V hat is the direction of movement, and CD is this drag coefficient. And we'll get into some realistic numbers later on that. So as we're exploring this terminal velocity, we have acceleration is equal to 0 meters per second squared. And so I'm going to make down positive, and let's just look at the simplified form of F equals ma. The force down is the weight, and then the drag force is pulling back on it. That's equal to 0. If we add FD to both sides and substitute that formula in, we get mg is equal to 1/2 rho CD a v squared. Now, I have a little subscript t here because this is the terminal velocity, because that is the situation I'm working with right there. So Vt is equal to square root of 2 mg over rho CdA. Now, I do want to point out that we are dealing with the drag being related to the speed squared. If the object is small enough, it's not really related to the speed squared. It's more related closer to speed. And matter of fact, in different situations, this exponent could be slightly different numbers, but this is the generally accepted one for macroscopic objects. We have a number of things here which are specific to a situation. And so what I'm going to do is I'm going to do a little substitution here and just break it down into simpler terms. I'm going to let K equal 1/2 rho CdA. In other words, the drag force is directly proportional to V squared by this proportionality constant, which I'm calling K. And so my terminal velocity is the square root of mg over K. So that is the situation for acceleration equal to 0. And you can put vector symbols over both if you wish, but either way. So let's look at the situation. The magnitude of the acceleration is not equal to 0. So weight minus the drag force is equal to mass times acceleration. So the weight minus kv squared is equal to m dv dt. And we basically have set up so that we're going to need to do a little calculus here. The force, which is directly related to the acceleration, is related to the speed, and acceleration and speed are related. And so we'll end up with, in essence, a calculus problem. Dividing by the mass, we get g minus k over m. V squared is equal to dv dt. Mass cancels out on the right-hand side, and on the left-hand side, it cancels out in the first term and shows up in the second term now. Factor out negative km. I'm left with negative gm over k plus v squared is equal to dv dt. And so if we then get the v squared terms on one side, or we get this over on the dv side and bring dt over, we get this. I'm now going to let b squared equal gm over k, and so b is equal to the square root of gm over k, which is just my terminal velocity. That's convenient. And so now we have negative k over m dt is equal to dv over v squared minus b squared. This is nothing particularly significant math-wise other than these are the steps that you go through. I mean, it's a classic solving technique. Assuming that we're starting at rest, that we're dropping the object, it starts at 0, goes to some time t, and then 0 to some speed v. And I know for the math purists out there, the fact that I have dv, v, and t, dt is sort of taboo in the math world. However, in physics, it's common notation, just recognizing that this v is some final speed, and these v's are variables. That t is a variable, that t is at some specific time t. Integrate. Now, in order to do this integration, there are a couple ways of doing it, but the physics approach is to look it up in a table of integrals and solve it that way. Or you could go through a much more complex method, but looking it up is fine in physics. And so we have negative k over mt from 0 to t, and then is equal to the natural log of v plus the square root of v squared minus b squared from 0 to v. So we have the natural log of, well, you plug in v and then you plug in 0, and this term over here just becomes v because you get the square root of v squared, which is v. And when you're subtracting logarithms, it's the same as dividing the meat of it. And so we have negative k over mt is equal to the natural log of v plus the square root of v squared minus b squared divided by v. Now, solving for v is a nuisance here, and so this is not necessarily a simple thing to go about, and so we're going to approach it from a slightly different point of view, but that's a classic technique, and then if you could solve for v, you're good to go. Going back to this step right here, let's explore this one a little bit, because there is a different way of approaching it, and let's do it. And we're also, later on, we're going to get this as well. And I write through those steps, but just you'll see it again. But looking at the right-hand side here, we have the integral from 0 to whatever that final speed is, or the speed which we'll find as a function of time, is equal to dv over v squared minus b squared. And factoring the b squared out, we have the integral from 0 to v of dv over v over b squared minus 1. Now I'm going to do some u substitution, let u equal v over b, and so du is 1 over b dv, or dv equals b du. 1 over b, integral from 0 to v over b, du over u squared minus 1. Factoring a negative out, we get negative 1 over b, integral from 0 to v over b, du over 1 minus u squared. Now, this is also something you can look up in the table of integrals. So this integral right here, the integral of du over 1 minus u squared, is the arc hypertangent of u. So we end up with negative 1 over b, arc hypertangent of u, from 0 to v over b. This is a valid integration if u is less than 1. So let's take a look at that one. So we want u to be less than 1, which means v over b is less than 1, which means that v times the square root of k over mg, from what the value of b is, as defined on the previous page, is less than 1. And b is terminal speed, so v over the terminal speed is less than 1. Is that, if that's true, then that's true, and yes, it is. The terminal speed, or terminal velocity as it's usually said, but the terminal speed is an asymptote, and so we would get closer and closer to it without actually hitting it, so that will indeed be less than 1, although it gets closer and closer to 1. Having established that, we can now go to plugging in v over b into the arc hypertangent, and we end up with this. The arc hypertangent of 0 is 0, and so that simplifies down to negative 1 over b times the arc hypertangent of v over b, which is equal to, don't forget what we had on the previous page, the time piece of it, the integral from 0 to t of negative k over m dt, or negative k over m times time. Now looking at these two right here, multiplied by negative b, so the negatives will cancel out and b goes up on top, and so arc hypertangent of v over b equals bk over mt, which is plugging in expression for b, square root of gm over k times k over mt, which then simplifies to this. We end up with this. I know that the terminal speed is the square root of mg over k, which is g times the square root of m over gk. So the square root of m over gk is just the terminal speed divided by acceleration due to gravity, or the square root of gk over m, which is what we have right there, is just g divided by the terminal speed. And so the arc hypertangent of v over b is equal to g over vt times time. And that last step, we have v over b is equal to the hypertangent of g over the terminal speed times time. And if we solve for v, we get b times the hypertangent of g over vt times time, which is vt, because b and vt are the same thing, vt times the hypertangent of g over vt times t, which is the velocity with respect to time. So we have a function now to describe the speed of an object as it falls, or velocity if you want to put a direction downwards onto it. Don't forget, we do have an expression for the terminal speed based upon the physical characteristics, based upon the density of the fluid, based upon this coefficient based on the material and shape of the object, and then the cross-sectional area, as well as the mass and acceleration of gravity. So let's plug in numbers. So some drag coefficients. I was looking around trying to find realistic values for the drag coefficient, and I got a range going from 0.04 to 2.2. And a human, if you think about a human skydiving, the drag coefficient's about 1, and this is belly down as you're falling. Skydiver with head down would be around 0.7, and so we have a terminal speed of around 54 meters per second. And so let's plug in, find out what's happening. So if we have a person who's falling, put a mass of about 90 kilograms, which is roughly my mass at the moment, what would be the drag coefficient? Well, my cross-sectional area is about 0.6135 square meters, and this is based upon some measurements that I had done for another video, which you might or might not have seen. G is roughly 9.8 meters per second. I am skydiving. It is going to increase as I fall, but it's not going to increase significantly, so this is close enough. And the density of air is about 1.225 kilograms per cubic meter. Again, it does change depending upon how high up I am going, but again, close enough. So my drag coefficient would be 2 mg over rho a times my terminal speed squared, which puts it about 0.805, which puts it in the ballpark here. So this was done if I'm outstretched. And watching various videos of people skydiving, most people are bent at the knees. So that would be falling with my legs outstretched like that, but bent at the knees. Because it seems it's really difficult to keep your legs flat out. So when you do that, my cross-sectional area drops, and so my drag coefficient, if you go through the same process, turns out to be 1.028, which is, as they're saying, about 1.